Hello everyone, welcome to my class. In today's class, I'm going to cover derivatives and integrals of vector functions. So quick recall, in our last class we defined vector functions. We found the domain, limit and continuity of vector functions, and now we try to put a calculus on vector functions. So that means how we define derivatives and antiderivatives of vector functions. So let's begin the class. Calculus with vector valued functions. Definitions: we define the limit of vector valued functions component wise. Similarly, we take the derivatives of vector valued functions again component wise. So here d over dt of vector functions rt equals to r prime t. This equals to derivatives of first component, derivative of second component, derivative of third component. Similarly, we integrate the vector functions component wise. So the integral of rt becomes integral of ft, means first component, integral of second component gt, integral of third component ht. I hope this makes sense to you all. A quick side note: the definite integral a to b rt does not give the area under the curve given by rt, but in calculus 1, the definite integrals of fx gives us the area under the graph of y equals to fx above the x-axis bounded between x equals to a and b. The definite integrals of the derivatives r prime t is simply the displacement rb minus ra by fundamental theorem of calculus. C, r prime t is called the tangent vector to c at t. So that means the first derivative of rt, means the first derivative of position function, is the tangent vector. The unit tangent vector is denoted and defined by the vector. This is the uppercase T equals to the tangent vector r prime t divided by its magnitude, which is simply the velocity over speed. Awesome. Now the derivative rule for vector valued functions: derivative of the sum or difference equals to sum or difference of the derivatives. Derivative of constant times vector function equals to, you can pull the constant outside, so constant times the derivative of vector functions. Product rule. So here the ft is a scalar function and ut is a vector function, so we use the product rule here. So the first function's derivative, keep second function as it is, and plus keep first function as it is, take the derivative of second function. Similarly, in the dot, derivative of the dot product of two vectors, derivative of the cross product of two vectors. Chain rule. Quick remark: if a curve lies on a sphere with center at origin, then the tangent vector is perpendicular to the position vector, that is r prime t is orthogonal to rt. Let's do a quick proof here. Note that the absolute value of rt is constant. So this implies, let's take the dot product rt with itself, which is magnitude of rt square, which is k square. Then apply the derivatives here. So you apply the derivatives here. So the dot product, I can use this formula. So this gives me first function's derivatives, keep dot rt as it is, and plus keep first rt as it is, and take the then dot there and take the derivative of rt. That means I can have this 2 times rt dot r prime t equals to the k square is constant, becomes 0. So divide both side by 2. It gives us rt dot r prime t equals to 0, implies rt is orthogonal to r prime t, or r prime t is orthogonal to rt. So here 2 times rt dot r prime t equals 0. So dot product 0 implies R prime t is orthogonal to RT. Awesome. In other words, a vector of constant length is perpendicular to its derivative. Let's move on. Now, let's do some examples. First example, given the vector equations, answer the following questions A through F. Sketch the plane curve with the vector equations. So let's try to eliminate the t and then write in Cartesian form, then it's easier for us to graph here. So here x equals to et, y equals to e to the power negative 2t. We can rewrite this y equals to e to the power negative 2t equals to e to the t times this minus 2, the power. So y equals to x to the power minus 2, which is same as y equals to 1 over x square. And by the way, x is et is positive, so x is strictly positive. That means only this branch, right? So into the graph of y equals to 1 over x square when x is positive is this graph here. So and let's put the orientation, because this is a vector equations. We need to know which direction the curve is tracing. So now let's check t equals to 0. When t equals to 0, then xy equals to x is here e to the 0, y is again e to the 0 when t is 0. That means I will get 0.11. So then I'll get 0.11 here. And if t equals to 1, I'm increasing t value, then here e to the 1, e to the power minus 2, which turns out to be 2.7, 0.14. That means 2.7 means we are somewhere here, and 0.4 somewhere here means we are going this way. So our orientation of the curve is this. Great. So part B, find the derivatives of RT, means we can take the derivatives component wise. So here is et derivatives itself, and the derivative of e to the power negative 2t becomes negative 2 times e to the power negative 2t. Part C, sketch the position vector RT and the tangent vector R prime t at t equals to 0. So solutions, so here RT at 0 is simply 1, 1. We already computed here and in the vector form. And R prime t at 0 turns out to be 1, minus 2. Then let's graph those vectors. Here's R0 is this vector here. So 1 from the origin here. So 1 and go 1 up. And always we sketch the tangent vector starting at the curve. So starting at the curve here, 1 unit to the right minus 2 unit means 2 unit down. So that means from here 1 unit to the right positive and 2 unit to negative. Y values means go down 1, 2. We are here. That means this is our tangent vector R prime 0. I hope this makes sense to you all. Now let's move on. Part D, find the unit tangent vector at 0. So apply the formula. So the formula for the unit tangent vector is simply the derivative of r over magnitude of r prime. That means, and evaluate at t equals to 0. So r prime 0 over magnitude of r prime 0. R prime 0 we computed here, 1, negative 2, and find its magnitude. Its magnitude is under the radical 1 square plus minus 2 square 2 to 4 plus 1 5, radical 5. So let's divide r prime 0, we also have vector here, by radical 5, which I did here, 1 over radical 5 r prime 0. I hope this makes sense to you all. Let's move on. Part E, find a vector equations for the tangent line to the curve at 0. So to find the tangent line, means the equation of a line, we do need two informations. One is a point and one is a parallel vector. So let's find point here. The point is when you put t equals to 0, the corresponding point is xy is 1 1, because our rt, this is the x value, this is the y value. So when t is 0, this is 1, when t is 0, this is 1. So our point is 1 1. And for the parallel vector, we take the derivatives here, so which already found here. So r prime 0, that's our vector, so 1 minus 2 here. Then the vector equation of the tangent line is, so the vector equation of a tangent line is x equals to x0 plus sv. I use a parameter s here because t is already used. So x is arbitrary vector xy equals to x0 is 1 1, so 1 then plus 1 times s comma 1 plus minus 2s, so 1 minus 2s here. I hope this makes sense to you all. Now let's move on. Let's do part F. Let's find the integrations. Let's integrate the vector functions rt. We integrate component wise, so we integrate et, we integrate e to the power negative 2t. So integration of et is itself. Integration of e to the power negative 2t becomes negative 1 over 2 e to the power negative 2t and plus constant of integrations, which is a vector here, the constant vector. I hope this makes sense to you all. Great. So let's move on. Example 2. Consider the helix rt equals to cosine t sine t t and answer the questions A and B. Find the unit tangent vector of rt at t equals to pi 4. Begin the solutions. So then unit tangent vector at pi over 4 is equals to r prime t over magnitude of r prime t valued at t equals to pi 4. Let's find r prime t. Let's find its derivative. So we take the derivative component wise. Cosine t derivative is minus sine t. Sine t derivative is cosine t. T derivative is 1 over the magnitude of the derivative. So here at t equals pi 4. So find sine pi 4th is 1 over radical 2. Cosine pi 4 is 1 over radical 2 and 1. Then in the magnitude, we can take the magnitude of 1 over radical 2, 1 over radical 2 and 1. So 1 over radical 2 is square 1 over 2. 1 over radical 2 is square 1 over 2. Then 1 is square is 1 under the radical. I hope this computation makes sense to you there. And we evaluate at t equals to pi 4th for the numerator. And the next step, minus sine put here pi over 4, which is minus 1 over radical 2. Cosine pi over 4, 1 over radical 2 and 1 all over. So this turns out to be radical 2. And then here put 1 over radical 2 outside, and 1 over radical 2 times radical 2 is 1 over 2, then minus 1 1 and then radical 2. So this is the unit tangent vector at equal to pi 4th to the given helix. Part B. Find a vector equations or parametric equations for the tangent line to the curve at t equals to 5 pi over 6. Awesome. So here we are finding the equation of tangent line. Means equation of line, we need two informations. One is a point, one is a parallel vector. So point, put t equals to 5 pi over 6, and the corresponding point xy will be our point for the equation of tangent line, and find the derivative r prime t and evaluate at t equals to 5 pi over 6. This will be our parallel vector. When you have two informations, point and parallel vector, then we can easily find the equation of line in parametric form or in vector form. Great. So here, so t equals to 5 pi over 6 corresponds to the point minus radical 3 over 2, 1 over 2, 5 pi over 6. So this point, just put it here. So cosine 5 pi over 6 is minus radical 3 over 2. Sine 5 pi over 6 is 1 over 2 and t equals to 5 pi over 6. Next, let's take the derivatives. So r prime t is minus sine t, comma cosine t, comma 1. Evaluate the derivative at t equals to 5 pi over 6. It gives us this vector. So then this vector is the vector we are looking for, and we already have the point. Then our vector equations of the tangent line turns out to be this formula, which is xyz equals to this vector here. If you are writing separately, this will be our parametric form. Just quick visualization here. I hope this computations and this visualization makes sense to you all. Now let's move on. Example 3, solving the differential equations. So example 3, solving differential equations. So find the RT, the position functions, if we know the derivatives, means if we know the velocity here, r prime t, given vector, and the initial conditions are at t equals to 0 is this vector 1, 1, 1. Solutions. So here rt equals to the integration of r prime t. So that means integrations of each of these component functions. So integration of 2t is t. Oh, this should be t square. So this should be t square here. Integration of et is simply et, and integration of t times et using integration by parts, it turns out to be t times et minus et, and plus this is the constant of integrations, vector c. I hope this makes sense to you all. And the next step, let's find the value of c using these initial conditions when t equals to 0. This is the vector given to us. This is t equals 0. That means put t equals 0 here. So this is t square. So t square becomes 0. E to the 0 is 1. This is 0. This gives you minus 1 plus c. So then c equals to subtract this vector from this left hand side vector, which gives us 1, 0, 2. So our vector c is, we found 1, 0, 2, and put this value back here. Then our rt is t, et, tet minus et plus this is the c vector we found here. And then add these two vectors. We add the two vectors component wise. So the last step here, t plus 1, et plus 0, tet minus et plus 2, which is here. Great. I hope this makes sense to you all. So we finish these sections. Thank you.